let's take a look here. Hopefully the identification was pretty straightforward now. The first one is going to be ellipse. How do I know it's not a circle? Because the two numbers are different. That's it, right? The second one's going to be hyperbola. I like it. And the third one's going to be circle. I like it. Because this third one's got equal coefficients on the xy pieces. So that's why I know it's going to be a circle. So let's see this first dude. So we know it's an ellipse. Now, the official term for the longer axis, the longer piece of the ellipse is called the major axis, and you have the minor axis for the shorter one. Does it really matter what we call it? Not really. But in case you see that in the homework, the semi-major, semi-minor would just be half the distance. Or the semi-major would be half of the longer distance, and the semi-minor would be half of the shorter distance. So why do we call it? Why do we pay attention to that? Because when I look at 9, what do I really use? What number do I use from that? 3. So I want to go out 3 and out 3. So the semi-minor axis length would be 3. So what is the total length going to be? 6. We'll have a 3 out one way, 3 out the other. Like it. Just got to be careful, because if your center is not 0, 0, that number actually tells you how far to go from the center. It doesn't tell you where to go, it tells you how far to go from the center. Here the center is 0, 0, because there's no xy pieces I've got to put together. I've got nothing inside. So the length of the x-axis, 6. Because this is 3, this is going to be 5, so the total length on the y-axis is going to be 10. So the major axis length. The center, of course, like I just said, 0, 0, because it hasn't been shifted anywhere. And the foci, it was a really good question. The book tries to be general, which I don't. I feel bad for anybody who tries to be general stuff. It's just the bigger one minus the smaller one, to keep it real, right? So it doesn't matter what A and B are. So c squared equals 25 minus 9. 16, then c is 4. So we'll point out, once you graph it, you can tell where the foci have to go. They always have to be on the major axis. Yes?
So for the homework, when we're writing down what the foci is, do we want to put it in intercept form?
Yeah, so it's going to be, so in this case, we're going to see in a minute. Well, let's graph it, and then we can see where these go. Because this really right now is a length. So when you take into account what the center is, although this center is 0, 0, thankfully, which makes this an easier problem. If the center wasn't 0, 0, I would just be counting, A, B, and C would be counting from that center. So then I want to do that first, and then I can just say what point I'm at. Right? So where am I at? Blah, blah. So on the x-axis, I'm going to go up and down 3. On the y-axis, I'm going to go up and down 5. So I can pretty much draw my poor little ellipse dude. I'm so sorry, ellipse dude. Help me as tomorrow. So there's that. Now, for the foci, I just want to go up and down 4 from the center. Why up and down? Because that's the major axis. That's the longer one. So I'm going to go up 4, put an x, down 4, put an x. So where are my foci? This is going to be 0, 4, plus or minus 4. That's where the foci are.
And so if it was the other way, it would be plus or minus 4, 0?
Exactly. Exactly. If the major axis had been the x-axis in this case, then we would have done everything and just turned around with plus or minus 4, 0. 11. So that's why we'll see in a minute the vertices question for a hyperbola is sort of related to that. It depends on which axis does it sit on. Okay, cool. And how do you kind of check this? You could, if I put a 1 in, let's try this out. If I put a 1 in for x, I get 1/9 plus y squared over 25 equals 1. Subtract 1/9, I get y squared over 25 equals 8/9. Multiply by 25, I get y squared equals 200 over 9. If I square root that, let's see, I'll get 10 rad 2, I'll get like 14 over 3, whatever the hell that is, it's like 4 point something. So once you go up to 4 point something, it looks like if I would have drawn this correctly, it would have. Yay. So you can always plug points in. You can always just plug points in to see if you got close to where they should be. You're not going to be perfect because we're just using these 4 points to fill it in. I'm not looking for perfection. Okay. So the second dude, we already identified it as hyperbola. Somebody already noticed it's not quite written in the right way, and this is just a common problem. X squared is over 1. So then this is related to 4, this is related to 1. We already know it's a hyperbola. It sits on which axis? Y-axis. That's where it's going to actually hit the y-axis because it's not allowed to have x-intercepts. So the vertices are going to be on the y-axis. So how far out do I go on the y-axis?
8.
Well, okay, so the total length is going to be like 8 for that across the rectangle. But I go up and down 4. So it's going to be a repeat of these foci here. It's going to be 0 plus or minus 4. Let me stop there for a second. The vertices of hyperbola are points that it actually goes through. So there are those 2 other points that we put on for our rectangle, but they're not really points on the graph. They're just to make that rectangle. So what do I mean by that? Well, the center, real quick, of course, is 0, 0, because it hasn't been shifted anywhere, unlike this one. This will have a different center. And the foci, now, we didn't do, I don't think we did this one, but can you imagine, this is the point I was trying to make earlier with the ellipse, it's got to be inside. It was a minus, so it was less than its vertices. This one's got to be kind of outside, so this is going to be c squared equals a squared plus b squared. And thank God for that. It doesn't matter what the hell you call a and b. You're adding it. So the foci c squared equals a squared plus b squared. So c equals square root of 17. So it'll be up 7, there's root 17. Down root 17. I like it. So let's try to graph this bad boy. So I got my vertices at 4 up and 4 down. I got my foci at square root of 17, which is just barely over square root of 16. So it's going to be just right outside of that. Right there next to it, basically. The other 2 positions, not really points on the graph, are going to be related to the x-axis. I just want to go 1 out on the x. So 1 out here, and 1 out there. And then you make your little rectangle. Now, so the whole thing I'm doing right now, you would do it exactly the same way if it had been shifted. You just find the center and then just count from whatever that point is to make everything. You just count from that center. So right now I'm counting from 0, 0 because that's the center. So if it's a different center, it doesn't change the work. You just start counting from that center. Same work. So here's my little rectangle. Yeah. And then I can do my little asymptotes. And then, see how that focus is really close? So it's going to be, so that's why it's really like, and on the other side, if it was the other way, it would be like this, right? And real quick, the focus would still be square root of 17, even if it opened this way. Because a and b would still be 16 and 1, right? A squared, b squared. So the focus would be way out here, so the further away it is, the more I'm like, oh, okay. The closer it gets, I'm like, oh, shit. And then it, so that's why if their focus is so damn close to that point, it's like this. It's like, oh, shit. I don't know if that helps. Yes, sir?
So for the hyperbola, is there any way for the focus to be inside of that rectangle?
No. See how I said that? If you start pulling complex shit in, anything can happen. But real, plain, real stuff, no. Impossible. Just because it's a plus. You realize how you bring complex stuff into play, anything can happen. Shit. So now you just gotta whoop, whoop. You can make whatever sound effects you want. Coolness. So if this would have been just turned around, none of the work I did would be different until that very last thing I just did. I would have done it over here instead. That's all. I like it. So this last dude should be the quickest dude, actually. This is obviously a circle for two reasons. One, it is, and the other one is I haven't done a circle yet. Center is at -2, 1. I love it. The opposite when it's inside with the letter. That's how it's shifted. And the radius is 3. So you find the center, -2, 1. That's the center. And then you just count 3 out from in the 4 cardinal directions. Good. 1, 2, 3. 1, 2, 3. 1, 2, 3. And 1, 2, 3. And then you hopefully do better than Jeff at making a circle. Oh my God. If I go to hell, I'm going to have everything I've ever drawn just down there beating me forever. You didn't really do me well. Shut up. Okay. What did you do in class that talked about shapes beating my teacher forever? No. Oh, okay. Well, that's different. All right. Now, obviously, I'm not going to get as deep into this as I can because you're going to do a lot more with this in pre-calculus if you do take pre-calculus. If you don't, you're just going to do this much, which is great. You still know they exist. There's a lot in the book reading about comet orbits and stuff like that, planetary orbits. Unfortunately, they don't talk about eccentricity in here, but all eccentricity would be is C, let me see if I remember, C divided by A, but it's got to be, shoot, I wish they would have had it in here. But they don't have it in here. You don't have to worry about eccentricity. It is a measure of how far from this being a circle it is. I do want to do just the smallest bit out of chapter 14 before I let you out of here. My poor people. You know, like this is how we get rewarded for being here. What did I put back? Oh yes, I'm going to reverse it. So let me do this. You could be looking at that sheet, but let me have you think about this first. So you've seen stuff like this in your life before, where they ask you, tell me the next couple terms in a sequence. Poor little dude. All right. So let's start off nice. If I said, tell me the next couple terms in the sequence, what do you think it would be? Yeah, it's going to be 17, 22. Why? What did you notice about 2, 7, 12? I kept adding 5. Now, to be honest, if you sat there and thought for a while, you probably could come up with a different pattern between 2, 7, and 12. It's not impossible. If I don't give you enough numbers, there are multiple possible answers. And I often get them when I didn't even think there was. I give somebody this, and somebody tells me these weird-ass numbers, and I sit there and think about it like, holy shit, yeah, that works. So there are possibly multiple answers to this. So what about this one here? What about it? Good. So this is obviously not adding or subtracting the same thing over and over again. This was a really easy one, just added 5 forever. This one's not addition, this is based on multiplication. I love it. So this is where I multiply by -3, multiply by -3. So the next one would be negative 54 times 3. 162, cool. And then you multiply by -3 again, and you get 486. Right? And it could keep going forever. So these are, you know, you've already heard the word sequence before. These are sequences. One of the coolest sequences in existence. Believe it or not. This is one of the trippiest ones. It's not this, it's not this. It's neither one of these ideas exactly. It's a little play on this one, I'd say, just to give you a little hint. You don't keep adding the same thing. So I have to start with 1, 1.
So it's 1 plus 0, and then it's 1 plus 1.
Good. 1 plus 1 is 2.
Yeah.
1 plus 2 is 3. So to get the next term, you add the 2 before it. You guys with me? Anybody ever seen this sequence before? You have? Do you remember what it's called? Starts with an F. Yeah. Fibonacci. Fibonacci. So this is he had a thought experiment where he said if you did put some rabbits in a room, gave them some food, and let them go at it, how many rabbits would there be after so many times? Well, they start with 1 each, and then they have a baby, and then they have another baby, and then those are old enough now to have their own babies. This also, I can't even describe. That's where it first came from, was a thought experiment about rabbits. But then, if you walk around and you look at trees, they will often have one branch, and then they'll have, the one main thing, and then they'll have 2 branches, and then they'll have 3 as you look across. So if you look across, 1, 2, 3, and then they'll have, this one goes like that, 5. It's crazy. Healthy trees that haven't been chopped or something. I remember the first time I ever heard about this, and I was walking around looking at trees for a while. I'm like, holy shit, it's freaking true. This shows up in pine cones. This shows up in music. Do you guys have an alarm wake up in the morning? Is it music or is it one of those wah, wah? Yeah. So the frequencies used to create that sound are frequencies that would not be found in the sequence, or the ratio of the frequencies wouldn't be close to the ratio of the numbers in the sequence. So those are not pleasing to the ear. Things that do have ratios that are similar to ones in this sequence are pleasing to the ear. It's weird. Yeah. I mean, this is the intersection of math, psychology, art, music, finance. There's actually a Fibonacci rule for stock trading that my friend Sean, who has a lot of money, who could do this. Through the recession, he made money because he followed the Fibonacci rule, which is all about looking to see how many times did it have a dip, and then that is a way to predict when it's going to have a huge dip. And it doesn't seem like it would be true, but it is. It's crazy. He actually made money during the recession because he followed this. He didn't make like a ton of money, but he didn't lose money. That's the key. Anyway, so the Fibonacci sequence, you could study it for a freaking lifetime. If you go to a bookstore and just look up Fibonacci sequence, you'll see a bunch of books about the Fibonacci sequence. Golden spiral is related to it, the golden rectangle, the golden ratio. It's insane.
So when did you do that?
When did Fibonacci do that? I think it's like the 1700s. Don't quote me on that. Do they even talk about Fibonacci in here? I would hope so. Oh well, you guys can look it up. You got Google nowadays. So it's Fibonacci, Fib-O-Nacci. So you can search it. And if you went to Google and you typed in Fibonacci blank, Fibonacci surfing, there's actually somebody who made a surfboard based on the Fibonacci sequence. I don't know if it does any better than a normal surfboard, but still. Fibonacci and music, there's a lot of ties between the two. Fibonacci finance or whatever, that would come up with the thing I told you about. It's insane, or alternately golden ratio. Something. Right, so what would be the next term of the sequence? 55, and then 89, right? So if you divide terms one by the one before it, it eventually becomes just a single number. It's always 1.6108, right? Or is it 1.618? I can't remember. There's that. If you keep dividing, what is 89 divided by 55? It'll be close to that. It's probably like 1.62 or something. 1.618? There you go. And if you kept going in the sequence, it would keep coming out to this number. That's why we actually gave it this symbol. We gave it this symbol, which is a Greek letter phi, or phi, depending on how you feel. All right. I've said plenty enough about that, I think, right? You guys like, yes, please stop. we're not going to do a lot with this, but obviously this is a kind of a nifty thing to look into. We are going to do one section in chapter 14 deals with these two specifically because they are very fundamental types of sequences based on addition, based on multiplication. So we're going to actually create formulas to predict, like if I wanted to know the 907th term in the sequence without just adding 5 900s more times, there must be a formula because it's a very basic way to build the sequence. There's a formula, and we're going to create the formula. The same thing for this. We're going to create the formula. We're also going to talk about an urban legend in math. That's going to come up in chapter 14 because you have me. I'll tell you a little urban legend about a famous mathematician. It's not going to be good enough to make a movie out of it, but I think that's probably plenty. So if you want to get a little head start, you can look through this side of the conic sections handout. Otherwise, you can just wait for tomorrow. All right, guys, that's plenty, I think.